Uh, Hello, everybody. This is magnetic circuit part 2. Under this, we're going to solve problem number 2. It's a continuation of part 2. So, uh, problem number 2, we're going to see how to solve. If you look at the lecture sheet, the core is actually divided into two parts. One is the steel sheet. It was like this. So it was going through like that and this. So the current was flowing through this was I, and N is the number of turn, which was given 50 turn, and the upper part of this was steel sheet, and the lower part was made of cast iron, and the flux lines flowing through the core was like this, up to this, the red one, and then under the blue cast iron sheet it was flowing like this. But it is the same phi flowing through both because these are in series. Same phi is flowing through that. Question given here, you can see that LAB, this is what is your A, B, C, D, E, F. So if you go there, LAB equal to LCD, LEF, LFA equal to 4 inch, and LBC equal to LDE equal to 2.5 inch. This is what the given parameter, and the A is given there as 1 inch square, and phi, that is flux flowing, is given here as 3.5 into 10 to the power minus 4 Weber. Now all what you have to find is, you have to find, if you read the question in the lecture note, is given they determine the current I equal to what? So current I equal to what? That's what you have to determine. Now in order to solve the problem, all what you have to do first, you have to solution, draw the equivalent circuit first. Equivalent circuit, and then go ahead. So if you want to draw the equivalent circuit for this magnetic circuit, the equivalent circuit will look like this. For example, the input is coming from this, so you can say this is the F, which is Ni, and this is the core, first core, and this is the second core, and the reluctance for this one are SS, the reluctance for this one are Ci, and F. You know that in order to solve the magnetic circuit problem like this, you have to draw first the equivalent circuit, electrical equivalent circuit, which should be like this: voltage source first, then the reluctance RSS and RCI. These two you have to go for. So this is the magnetic force, and this is the reluctance for RSS, the reluctance for RCI, and a current like magnetic flux phi is going to circulate through this circuit. So in this loop, the current or the flux lines phi is flowing, and so this is plus minus, this is plus minus the voltage drop or magnetic force drop across RS and RCI. So according to KVL, if you apply the KVL, you'll see that this F will be equal to FSS plus FCI. Just like the lecture part 1, from there you come to know that this magnetic force F is nothing equal to Ni. Then also the magnetic force will be equal to H and L. So these two formula you already know from lecture 1. So from there we are going to write here as F equal to Ni, and FSS is HSS and LSS, and plus FCI is HCI and LCI. Now we already know the N is given there as a 50, and so this is a 50I. This is 50I minus equal to HSS. This value actually we need to determine from these things coming from the VH curve, and HCI we have to find from the VH curve in the last lecture. You have seen how to find it. Now that part we are going to find, and also we are going to find the LSS and the LCI. Now if you go for LSS and LCI, then LSS is coming here as equal to L EFAB. EFAB is equal to 12 inch is coming as, and if you convert into millimeter and then it's a meter, then it is 304 into 10 to the power 8 into 10 to the power minus 3 meters square. And LCI will be equal to LBCDA BCDE is equal to 5 inch, as you can calculate it. So it is giving you 127 into 10 to the power minus 3 meters square, and the cross-section area throughout is coming here as a 1 inch square. 1 inch square is going to be equal to 6.452 into 10 to the power minus 4 meters square. As you can see, 1 inch square is converting the meter square, and so your B. So you can write this value as from here you get the LSS and LCI, and you can substitute this value LSS as 304.8 into 10 to the power minus 3 plus HSF equal to what into LCI is giving you here 127 into 10 to the power minus 3 meters square. So all what you need to find here now is your HSS, what is this value, and LCI, what is this value. These two values you have to calculate next. In order to find the HSS and HCI, you need the flux density B, which coming from here as B equal to phi by A. So phi by A, you got a phi which is given in the last page. I have shown you the phi, and if you substitute the phi and the A value here, you are going to get approximately 0.54 Tesla. 0.54 Tesla you are getting. So the corresponding H's curve from this B, you are going to find the H. So HSS and LCI, these two ducts you have to find from the BH curve. So BH curve gives you these two values for steel sheet and the cast iron. So let's go to the BH curve for flux density B equal to 0.54. If you go with this BH curve here, 0.54 BH steel sheet, if you consider, also for this graph from here, if you can see, or from here also same, you can go with these things. Sorry, you can go with this, and this is the steel sheet. You can see from here the steel sheet is here, and there's an external curve here. So the current, the what do you call that, to the B flux density is 0.54 something, 0.54, which is here. 0.54 is here. So if it is here, its corresponding intersection is from here 0, approximately 300, so approximately 70 if you consider. Or if you go to the other curve, it's very similar. You can find 0.54 is giving you here, is going to give you 70 approximately. Whatever it is, you can just consider approximately 70 ampere turn per meter square. So if you write like that, the value is 70 ampere turn, 70 ampere turn per meter. So 70 ampere turn per meter if you write this H, and HCI, cast iron. For the cast iron, you can also find from here. The cast iron is this, the lower line is a cast iron line, and the 0.54 is here. The corresponding 0.54 is giving you something like 1500 and 1800. So we can consider it's approximately 1600 if we consider. Whatever the value you get, no problem. It's the more than 1500, less than 1800. So if we consider approximately 1600 meter per square ampere turn per meter, then these two values we already got. Now we can substitute these two values over here as 1600. This is 70, and this guard is 1600. If this is 1600 into this, and that is 70, then from this equation you can find the value of I, which will give you straight away 4.49 ampere. So you all can get this calculation. It's done. That's the solution to this problem we can find. Okay, now let's go for problem 3 according to the lecture note. If we can see the problem 3 problem, it's given like a transformer core is given like this, and there is a coil in the primary side and the coil in the secondary side over here like this. And okay, so in the primary side, the current flowing through that is I, and the number of turn is N1, I1 if we can say, and the current in the secondary side is I2, and the number of turn is N2. And the thing given here as and what happened due to this, a flux lines is flowing through this, and phi is flowing through this. Is the same flux lines is flowing, and you can see here that B, C, D is the flux lines direction. So what are the things given here? If we go, then we can see that the number of turn N1 is given here as a 60 turn, number 2 N2 is given here as a 30 turns, and then I1 is given here as a 2 ampere, and what is the other thing is given here is the cross-sectional area. A is given here as well as 0.15 into 10 to the power minus 3 meter square, and you can correct it if it's not clear in the sheet. And this cut is given here as a phi. Flux lines phi is given there as 0.15 either 1.5 into 10 to the minus 5, 1.5 into 10 to the power minus 5 meter square Weber. So Weber phi is given for flux lines, and your flux lines length L is given here as A, B, C, D. Is the total length is given here 0.16 meter. And what do you have to find? You have to find the value of I2 according to the lecture note. If you see, then you have to see that what you have to find is you have to find I2 equal to what? This is the question given in the lecture note. You can have a look of this thing. So if you go with this, then first, that is in your solution, you have to go for the solution. When you have to go, your first thing is you have to draw the equivalent circuit. And if you want to draw the equivalent circuit here, the first thing, equivalent circuit will be only one core, so one resistance will be here, and this is the two magnetic force, and this is one is an F1, another one is a F2 for the magnetic force induced into the second one, and this is the reluctance R. And this one you can consider as a steel sheet. This card is not given here, just considered as a steel sheet, so it is RSS if you consider. Then what we are going to get from here is Phi is flowing, which is given here as well. Just to all what you have to do from here, you can see the phi through the loop flowing, and from here you just write the KVL like last time what you have done. The KVL will tell you the F1 equal to this plus this. That is your equal to F1 equal to RHFSS plus F2. If this is the thing, then you are going to get N1 I1 and equal to HSS LSS, and this is F2 is N2 I2. This HSS LSS is this guard, which is this one. LSS is the total flux lines length, and this is the HSS, the flux magnetizing force for stainless steel. Now all what you see here, the things given here, N1 is given here as 60, I1 is given here 2 ampere, HSS you have to find it, LSS is given here 0.1, and N2 is given here as 30. All what you need to find is I2, and what in this equation you can find it I2 straight away if you know the value of HSS. Now what is SSS? That one will be your next step to do. Now HSS is coming from the BH curve. For that you need the B, and B is given here. B is given here. B will be coming from here, the phi by A, and your phi and A is given. Phi is 1.1 10 to the power minus 5, and this is given here 0.15 and 10 to the power minus 3. So what do you get from here? 1 divided by 0.1, that is your you are getting here 0.1 Tesla. Ultimately you are getting the H is like that, and this is going to give you the HSS from the BH curve. So the pH curve is going to give you the HSS. For 0.1 Tesla for stainless steel, let's go to the pH curve, and if you see the pH curve, and this is stainless steel SS, SS means this is your pH curve, SS, this is going to be, HS will be here. Okay, if you go to the pH curve, this got, and if you increase it, HS is this, and 0.1 is very small value you can get, or if it is coming here, you can find here 0.1 is here, HS curve is cutting here, which is approximately equal to 20 ampere. This is 20 of these things, just we assume 0.1 is giving approximately 20 ampere turn per meter. I'm talking about here 0.1 and cutting here to 20. So if you go to 20 ampere turn per meter, is the magnetizing force HSS. Substitute this value here as 20. If you put here the value 20, then your result comes here as a I2 straight away from the equation. If you calculate, and then your I2 will become straight away, if you do this conclusion, you will get 3.89, something like that, 89 ampere. So this is going to be your final answer for this problem. This is the way you can solve this problem number 3 of the lecture note I have sent to you. So this is all about the 3 problems that what we let's go back to problem number 2. In problem number 2, there is a little mistake. You can see here the LSS LCI are having meter square. I told meter square, and in fact this should be meter, not meter square. Only the area should be meter square. So just correct it. That should be fine. Now let us jump to the next problem. This is the last magnetic circuit problem. Let us have a look at the problem. This problem I'm going to send it to you by email, and you also can note it down. The problem is series parallel magnetic circuit problem. The series parallel magnetic circuit problem will be like this. One of the primary side is wounded by N turn, and there is a slot between this core, and there's one slot here, another one here. So due to this winding, the Weber flux lines produced, and that is flowing through these ways, the total flux line phi t, and it is dividing into 2 parts. One is a phi 1, another is a phi 2, and coming here together and joining again, phi t come back to join. This is the way the phi or flux lines is flowing. It's like the current is coming, total current is dividing into 2 parts like that. So second terminal current, there's a phi 2 is given here, is 1.5 10 to the 1 - 5, and the current flow through the primary coil is 1.75 ampere given. So what you have to determine is find the number of turn. This turns you have to find the number of turn for establishing the phi 2 equal to 1.5 10 to the minus 4 Weber per second. So this is what the question, and the given parameters are the L, B, C, D, A. A, B, C, D, E, F, A. This is the flux path. So L, B, C, D, E, B, C, D, E equal to E, F, A, B is equal to 0.2 meter given, and BE given here 0.5. Now cross-section area throughout same, and that value is 6 × 10 to the minus 4 meters square. So these are the given parameters, and the core made of steel sheet. So what we have to find is the number of turn due to this current produce this flux. What should be the number of turn we have to determine from this problem. Now let us go to the problem directly. The first thing what we have to do is we have to uh, see first what are the given thing. So in this problem, the problem is the series parallel magnetic circuit problem. So this is the series parallel magnetic circuit problem, and in this problem the given things are, as we have seen, the current is given I1, I is given 1.76 ampere. Then the LBCDE, which is LEFAB, is given here as 0.2 meter, and LBE is also given here as 0.05 meter. Now the cross section area A is also given here as 6.6 into 10 to the power minus 4 meter square. So these are the parameters given here. What you have to find is the value of the number of turn n equal to what. That's what the question is. But another thing also given, which is phi 2, which is given 1.5 into 10 to the power minus 4 Weber. The flux lines, phi 2 is given here. Now what you have to go for is, first of all, you have to find the equivalent circuit, as I told earlier as well. So the solution will be draw the equivalent circuit for the circuit. So equivalent circuit, if you want to draw, then you can see here the first thing is you have to have the source, which is the electromagnetic force, plus minus F is the producing force, which is N into I, and there is the reluctance, which is from EFAB, through which the phi t is producing, and BE is the reluctance. This is reluctance of EFAB, and the reluctance BE is here, and another reluctance BCDE. Another reluctance is BCE. So this reluctance is BE, and this reluctance is BCDE. So these are the three reluctance in series parallel combination, and the current flow, that is the flux lines, is phi t here, and this is phi 1, and this is phi 2. This is the current flowing through the circuit. So this is our series parallel. That's RBE and RCDE is in parallel with series REFE. It's two reluctance in series with that. This is how we get the equivalent circuit, and this is the loop KVL 1 you have to apply, and this is the loop KVL 2 you apply, then it should be fine. So what will be the equation for KVL 1 and KVL 2? Let us have a look first from here. If you go with this KVL 1 from here, then we can say that the KVL 1 will be coming from here as F equal to KVL 1 gives you F equal to F EFAB plus F BE, which gives you the NI equal to HEFAB LEFAB plus HBE plus LBE. This is KVL 1 you can have, and KVL 2 gives you the HFBE. KVL 2 is this one, and KVL 1 we have written already. So if you go with these things, you can see HB equal to FBCDE, which also give you the HBE LBE equal to HBCDE LBCDE. So these are the two equations you should get from these two KVL. And now in this case, the N you have to find, and I is given 1.76 ampere, and HBF you don't know, and LEFAB is already given here. LEFAB is given here 0.2, so you are writing here 0.2 plus HBE you don't know. I have to find it from the BH curve, and LBE is given 0.05, so that value you are given here. So these are the two things actually we have to find. In order to find, these are the two things. One is this, another one is this. These two guys, if you can find, then from here straight away you can find the value of N equal to what? Straight away N equal to what? Unknown things. Only HEF, HBF you have to find. In order to find these things, we have to jump to that, and here we can see also that the values given here, here HBE we don't know, but LBE 0.2, HBF we don't know, HBE we have to find it, we don't know, but HBF we don't know what is this value, and this LCBDE is 0.2, so we are going to put 0.2 here. That's done all what we have to find the HBDF from there. If we can find this, we can substitute this value here, then we can find the value of HBE. Once we can get HB, that HB can be substituted here, and then we have to find step by step the others. That's the thing. Now HBCDE, to find it, we have to go to this two things, HBDE, because HBDE is coming from 5, 2 and this thing. So HBDE, if you want to find, this comes from here, which is giving you the thing phi 2 is coming from phi 2, but phi 2 is equal to what? Phi B2 is coming from B2. This is coming from B2, and B2 equal to phi 2 by A. A is same throughout. So if you go for phi 2 by A, then it is giving you the values for phi 2 by A is equal to giving you the values of that is 1.5 in 10 to the minus 4 divided by 6, and that gives you 0.25 Tesla. 0.25 Tesla. So 0.25 Tesla is coming from here, and this 0.25 Tesla is giving you the B2, and B2, from B2 you are going to get the H2. H2 means HBCDE. That means it is coming from the BH curve. And our material is stainless steel, uses stainless steel, SS materials we are using here. So if you go for SS BH curve for HS materials, what is the H for 0.25 Tesla? If you go with that, for that you have to come to this curve. Now you can go with this BH curve. In this BH curve you have to look 0.25 Tesla gives you what? H. So for the steel sheet is the last one. This is the curve for steel sheet, and for steel sheet if you go for 0.25, This is 0.2, this is 0.25. So 0.25 is half of it, and you go with that, or go with that, and it's coming down here. It's almost 50. So we can say that this is almost 50 ampere turn. So we can write here, this gives you 50 ampere turn per meter. You can check in your own BH curve for this corresponding value. So we assume this is 50, this is 50, then we just substitute the value here 50, and after substituting the value, HB calculation gives you it is 200 ampere turn per meter. If it gives you 200 ampere turn meter, then this 200 ampere turn meter, from here you will find the, okay, this 200, one thing you can do, you can straight away substitute this value here. That means you are going to put here 200 ampere turn. And now our next job is to find HEFAB. For HEFAB, actually we need to find, for HEFAB we need to find the phi t, and phi t gives you the bt, and that b will give you the h. So if you want to find phi t, then one thing you should understand that the phi t is nothing but phi 1 plus phi 2. Phi t is nothing but phi 1 plus phi 2 is a summation of these two. So phi 1 plus phi 2, you already know the phi 1 value, which is given, phi 2 value, which is given here as 1.5. Phi 2 is 1.5 into 10 to the power minus 4 is given there. So only phi 1 you need to find, and the phi 1 is coming from HBE. HBE gives you the B2 or B1, or B1 you can say, or BBE also you can say, whatever, B1 or BBE, whatever you say will be giving you. So that comes from the BH curve. Again, the opposite thing, the BH curve gives you that value. So if you go back to the BH curve, from the BH curve for 200 ampere turn per meter gives you what flux density, BE or B1, that one from the BH curve we can find. Now look at this BH curve again, and if you go with the 200, where is 200? If you go with this 200 here, this is 200. So if you go along the 200 line, and intersecting here, over here, and corresponding value is 1.025. This is 1.0, 1.1 into 1.025. So we can get the value for this one is 1.025 Tesla. If this is B1 or BBE is 0.25 Tesla we get, then from here we can easily find the value of phi 1. The phi 1 value will coming from B1 into A. B1 into A. So that means you are going to get the value 0.01 into 1.025 into A. A value you substitute. Then phi 1 is coming here as, what's the value you can calculate phi 1 after multiplying these things is 6.15 into 10 to the power minus 4 Weber. So this is giving you 6.15 into 10 to the power minus 4 Weber. Together gives you 7.65 into 10 to the power minus 4 Weber. This is the phi t total you get. And the phi t is going to give you the value of BT or BEFAB. So the BT or BEFAB for this one, phi is giving this value like this, phi by A, phi t by A. This is the formula, you know. So flux density. So phi t is giving you now, what is the value? If you divide this by what? If you divide it by the area, then you are getting here 1.275 Tesla. So this is what finally you are getting for BT, and that gives you actually, this gives you the value of H EFAB through the BH curve again, because you got the B will give you the H, that is H. So this value, if you BH curve, you go back again for 1.275 T, there's a total thing, then you are going to get it like this. Go back to the BH curve again. So the BH curve, if you go, you can see here this 1.5 T, 1.275, where is that? 1.275 is coming here, over here, 1.1, 1.2, 1.275 is somewhere here, and if you go along this line straight away, intersecting somewhere here, and that intersection point is actually, it's a 1.75, 2.5 is coming in the middle of here, which may be the middle part of these things, which will be approximately 500 and 600, in the middle of 500 and 600. So maybe we can say it's a 550 or something like that. So maybe this thing we can assume as a 550 ampere turn per meter. So this is 550 if you consider HFE. Now look at it, this is our target HFE to substitute over here, and that value we are getting as 550. So HFE value, if you put here 550, then all our values HBE, HFE we can find, and then N equal to, straight away we can find this value is coming here as, if you do the calculation, it comes around 68.18, something like that, which approximately we can say 70 turn, a corresponding value, just N. So this is what the answer we can, you can keep the answer as a 68.18, also you get full marks. So this is how we can get the solution to this problem. You just repeat and try to understand. Hopefully it should be fine, and this is the way you have to solve the series parallel problem, and that's the final solution for this. Thanks for this. This is the end of magnetic circuit class, and go through these things and the practice problem I'm sending you. If you have any question, please send an email to me. Maybe I can entertain it over this Skype. Thank you very much for watching these things. Prepare one full question will be coming from this magnetic circuit, so everybody should be careful about it. Thank you very much.